This lesson deals with modeling a PN junction diode at high frequencies. You can find these notes in the ECE302 ebook in Chapter 10 starting on page 1. Suppose that we take a diode and reverse bias it. I'll show it here as a positive voltage from cathode to anode. What's going to happen? Well, the plus terminal is going to attract the negative charge, and the minus terminal is going to attract the positive charge. If an electron leaves here, it can't get back. So they just get crowded on this side or this side. We have a region here that's depleted of free charge, which is really just an insulator. Here you've got a conductor and a conductor separated by an insulator. Well, that's what a capacitor is. Now suppose that we increase the reverse bias. In other words, make V1 larger, call it V2. Again, these are reverse bias voltages. What's going to happen? Well, I have basically a bigger magnet here. I'm going to attract those negative charges more to this side and then positive more to this side. And I've now increased the distance between the two conductors that I have. In other words, the two plates of a capacitor. Capacitance is inversely proportional to the distance between the plates, so the capacitance goes down. Here's a plot of the reverse bias junction capacitance versus voltage. As the voltage goes negative, the capacitance gets smaller and smaller. Eventually it levels out. You can go slightly positive and still not be forward biased. That's what this part is over here. And eventually we're going to forward bias the diode, and that's going to be another kind of capacitance. This equation here is an approximation to the graph on the bottom of page 1 that was found experimentally. The term CJ0 is the capacitance when the voltage across the diode is 0. In other words, if you put a 0 here, no matter what this is or this is, you just get CJ0. This is the value of capacitance where we cross the y-axis. The term phi0 is called the built-in barrier potential. It has units of volts. This ratio is dimensionless, and then m is also a dimensionless quantity called the grading coefficient. But this is a very highly nonlinear equation with voltage across the capacitance. So one of the disadvantages of semiconductors is that we don't have linear capacitance, but very nonlinear capacitances typically cause distortion as the signal grows and shrinks. Now suppose that we forward bias that diode and apply a voltage across it where plus goes to the anode and minus goes to the cathode. And what's going to happen? Well, the plus terminal is going to repel the positive charge, and the negative terminal is going to attract it. So we're going to have positive charge moving in this direction, and likewise negative charge being repelled by this and attracted by this moving in this direction. So we get a double effect on the current flowing through the diode. As these holes are moving from the P side to the N side, suppose that we were to turn off the current, in other words, break the wire here, these positive charges would be trapped on this side. And they would recombine with the minus charges here and be neutralized. It's sort of like a capacitor being discharged. There's a similar effect going this way. When the negative terminal repels these, negative charges are here. If we were to break the wire, they would be trapped here and they would just recombine with the hole that's here and be neutralized. This is in words below here and on the next page. Because the capacitance associated with this effect is caused by diffusing holes from the P side to the N side and electrons from the N side to the P side, it's called a diffusion capacitance. Experimentally, it has the following relationship. The diffusion capacitance is equal to a constant tau sub t times the current flowing through the diode divided by eta v sub t, where tau sub t is called the transit time of minority carriers. The equation for I sub d is the Shockley equation, and if we're forward biased, we can throw the 1 away and just equal to I sub s times e to the v sub d over eta v sub t. As we increase the current, we have more carriers moving from one side to the other, and thereby increase the effective storage of charge, and so we increase the capacitance. Now what's interesting, back in Chapter 2, we showed that R sub d, that's just the AC resistance of a diode, is eta v sub t over I sub dq, and that's the reciprocal of this expression. The diffusion capacitance is equal to tau sub t divided by R sub d. If you cross multiply, you then have that R sub d times the diffusion capacitance is equal to tau sub t. Now tau sub t is a constant for a diode. It doesn't vary, but does depend on the value of these two, which are varying. What's interesting is that I sub d, as it increases, causes R sub d to decrease and causes the diffusion capacitance to increase. What I've got here are two nonlinear relationships, but their product is equal to a constant. That's really unusual. If you were to take a look at a time domain of this circuit when you forward bias the diode, you get an RC charging circuit. It looks very linear. But in reality, I've got the product of two nonlinear functions. We now have an AC model for a diode at high frequencies. If you bias a diode at some V sub dq and I sub dq, we have a resistance across that diode, but now a capacitance in parallel. The resistance we had shown previously to be an open circuit if you reverse bias it, and to be eta v sub t over I sub dq if you forward bias it. And then for the capacitance, we just saw that we had a depletion capacitance with this relationship, reverse bias it, and then a diffusion capacitance if we forward bias it. And this is the model for a PN junction diode at high frequencies.